Hi there, Mr. Sutton here with the BC Calculus 8.2 Extra Practice Number 1 Solutions on arc length. On this problem, I need to set up an integral and find the length of this curve along the interval from y is negative 1/2 to positive 1/2. So I'm going to need the derivative of this thing if I'm going to use my arc length formula. I'm going to need specifically dx over dy. So that's going to be, using our chain rule here, 1/2 times all this stuff to the negative 1/2 times a tail of negative 2y. Now, since I'm differentiating x with respect to y, I don't need to put like a dy dx or anything crazy over there. This is fine just the way it is. All right, so now let me do my general setup. I'm going to need the integral from negative 1/2 to positive 1/2 of square root of 1 minus dx over dy squared, dy. And since I've already defined what dx over dy is in this problem, it's this stuff right here, I can just go straight to the calculator on this one. So here I am in my y equals. I've put y1 as this derivative, this dx over dy, just so it's easier to plug things in. And quitting out of my y equals on my main screen here, just to plug things in, we've got the integral, math 9, from negative to positive 1/2, square root of 1 plus alpha trace to get y1 and square that. And I'll put a dx in here because that's how my calculator does things with x's instead of whatever other variable of integration you have. So enter, and that gives us 1.047. For this problem, I want the length of the curve y equals x cubed from x equals 0 to 2. For that, I'll use my arc length formula that has things defined in terms of x's, and I can tell from the answer choices that I need this one. So I need the integral from a to b of square root of 1 plus dy over dx squared dx. That's my general setup here. Now, I've got an integral from, it looks like 0 to 2, if I plug those in. And then I'm going to have square root of 1 plus the derivative of x cubed rather, so 3x squared. That's being squared. That doesn't quite match any answer choices, so I'm going to need to actually clean this up and simplify it. This will be square root of 1 plus 9x to the 4th, all of that with a dx outside. And that's going to match, let's see here, answer choice E. C is pretty close, except we have this random pi out there that we don't need. So choice E. For this problem, I want the length of y equals sine of 3x from 0 to pi over 6. So because I'm doing this with respect to x, I'm going to use this formula right here, where we have 1 plus dy over dx squared inside our square root. So I've got the integral from 0 to pi over 6, and I'm going to do 1 plus that derivative squared. Derivative, using our chain rule, that's going to be 3 cosine of 3x that I'm squaring in there. And I'll clean this up a little bit to match one of the answer choices. So if I'm squaring this expression, I really got 9 cosine squared of 3x. And then let's see here, that's going to be answer choice D. For this one, I want the length of y equals sine of x from 0 to 3 pi over 4. So for that, since I'm doing this with respect to x, I use the integral from a to b square root of 1 plus dy over dx squared, dx. So I have the integral then from 0 to 3 pi over 4. And let's see, 1 plus the derivative of y. Well, y is sine of x, so the derivative of that is cosine of x. So I've really got square root of 1 plus cosine squared of x, all of that with a dx. And this is going to match answer choice D. For this no calculator problem, I want to find the length of 2/3 x to the 3/2 from 0 to 3. So let me start by getting my general setup here. Since I'm doing this with respect to x, I have the integral from a to b of square root of 1 minus dy over dx with a dx outside, and that inside is being squared, that dy over dx. So let me see now. I've got the integral from 0 to 3, and dy over dx, using my power rule on the y function here, 3/2 times 2/3 cancels out, so we just have 1x, but this is going to be x to the 1/2 power. And I'm still squaring that, which means I really have the square root of 1 plus x, or 1 plus x to the 1/2 power. So now I'm going to have to take this antiderivative by hand. Using my reverse power rule, this bumps up to 3/2, and then I'm multiplying by 2/3, and I'm evaluating all of that from 0 to 3. So I have a 2/3. I have a little evaluation box with 1 plus x to the 3 halves from 0 to 3. Plug in stuff in now. This expression, I can convert this to the square root of 1 plus something and then cubing that. So we've got 2/3, and then inside we've got the cube of the square root of 1 plus 3 minus all of this stuff with 0 plugged in right there. Simplifying this a little bit, this is going to be, let's see, square root of 4, which is 2. Cubing that gives us 8. Still have a 2/3 out in front. And we've also got this over here is all just going to come out to 1, so minus 1. So this is 2/3 of 7, which is going to be 14/3, which is going to be choice C. On this problem, we want to know the length of the path described by these parametric equations from 0 to 1. All right, well, I'm going to use my parametric length formula. This one right here, integral from a to b, square root of, and now we have dx over dt and dy over dt being squared and added. So I have the integral then from 0 to 1, because this is with respect to t, so those are t values. And then dx over dt, just taking the derivative of x over here, that's going to just be 3. So 3 squared then. dy over dt, that's the derivative of 1 plus t squared, which is 2t, and again, we're squaring that. Cleaning this up a little bit, we've got the square root of 9 plus this is 4t squared, all evaluated from 0 to 1. And I'm just going to go ahead and pick an answer choice. That's going to be choice D. For this problem, I want the length of y equals x to the 4th from 1 to 5. So since I'm doing this with respect to x, let me use this formula, integral from a to b, square root of 1 plus dy over dx squared dx. So I have the integral then from 1 to 5, and dy over dx, that's going to be 4x cubed that I'm squaring inside here. Cleaning this up a little to match an answer choice, I've got, let's see, this is 1 plus 16x to the 6th inside the square root, and that's going to give us answer choice D. For this free response problem, no calculator problem, we've got the function f of x e to the 2x given in the graph here. And let's see, we've got the line x equals k, which we don't really know what k is, except that it's greater than 0. We want to evaluate, well, actually write but not evaluate, an expression with an integral that tells us the perimeter of this R region. But we can leave k in there, because we don't know what k is. All right, so let's just start with the easy stuff here. We've got 4 sides for this shape. We have to add them all together. This first side right here has a length of 1, so let's start with that. And then let's just go clockwise here. So actually counterclockwise. So down below we have this distance, which is just a distance from 0 to k of k. And then continuing along with this height here, that's just a height of e to the 2k, again whatever k is, so we'll add that in. Finally, we have to add the length of this arc here. Now this is a little trickier, but we can use our arc length formula. Since this is a function being evaluated with respect to x, we're going to do the integral from a to b, square root of 1 plus dy over dx squared. So I have an integral from 0 to k. That's my interval there. And then inside I've got the square root of 1 plus the derivative of this function here squared. The derivative of e to the 2k is just going to be, and now this is with, let's see, k is a constant. But this function in general has an x in it. So this is going to be 2e to the 2x that I'm squaring in there. All right, well, they said we didn't have to evaluate it. So we've got an integral, we've got some k in here, and it looks like then we're done. For this part of the problem, the region R is rotated around the x-axis to make a solid. We want the volume in terms of k. Since the entire bounded region is flush with no gaps against the axis of revolution, we are going to use disks on this one. So my area formula that I'm going to be integrating, we're going to say a of x equals pi r squared, where the radius, that's just the distance from the outer edge of the boundary to the axis of revolution. So that distance happens to correspond perfectly with the e to the 2x function. So we're just going to have pi times e to the 2x squared. I am going to have to evaluate this at some point, and it's a no calculator question. So I'm going to make this, let's see here, I'm doing integral from 0 to k of, I'm going to make this, pi times e to the 4x, actually multiply that exponent out with a little dx there. So integrating this area function now, I need the antiderivative. That's going to be, let's see, pi over 4 e to the 4x. So I have a pi, and I guess I've got a 1/4 in here with e to the 4x evaluated from 0 to k. So I've got all this with k plugged in, so e to the 4k, and then minus all this with 0 plugged in. I could actually leave it like this because I've got all constants and k's, which counts as a constant. But if I want to multiply this out, this is really pi over 4 e to the 4k minus, well, this is all just going to be 1 here for this e term, so just minus 1/4. For this last problem part, they're telling us the volume that we found in part B changes as k changes. We have a rate for dk over dt. We want dv over dt when k equals 1/2. All right, so this is definitely a related rates problem. We need a formula to start us off with here, and this is one of those where if you did not distribute things out and get kind of a polynomial looking thing for your volume in part B, now would be a good time to do so you don't have to use the product rule. So here's the volume that I came up with. Now I'm going to differentiate this thing implicitly with respect to time. So v, that derivative is going to be dv over dt. And for this next term, using our chain rule here, this is going to be, let's see, e to the 4k times 4 out here. So the 4 and the pi over 4 partially cancel, leaving us with just pi e to the 4k. But we're also going to have a tail of dk over dt because we differentiated a letter other than, other than t, which we never differentiate t in these problems anyway. Okay, so let's do another one here. This is going to be minus pi over 4, and then let's see, that derivative is actually 0, so we don't even need anything over there. Cool. All right, well, I guess it's time to plug things in and solve for dv over dt. So that means we need to plug in something for k and for dk over dt. Well, dk over dt they told us was 1/3. K they said was 1/2. So we have pi times e to the 4 times 1/2, all of that times 1/3. And this is all constants, so we're actually done. However, if you wanted to simplify it, this is really e squared, and we could write this, I guess, as pi over 3 if we wanted to. So pi over 3 e squared.